Hello everyone, this video is brought to you by the Atılım University OpenCourseware project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem about Chapter 8. According to this figure, a bob initially at rest is released. At the lowest position of the pendulum, the bob meets an unstretched spring and compresses it until it comes momentarily to rest. We are supposed to find the followings. The total mechanical energy of the system at the moment the bob is released in part A, the speed of the bob when it just contacts the spring in part B, and the maximum amount of compression of the spring in part C. We neglect the elevation of the bob during the compression in this case. First of all, we write the given physical quantities in SI unit system. Mass M equals 2 kilograms. Length of the pendulum L is 20 centimeters, but it should be converted into as 0.2 meters. Angle theta is 41 degrees and the spring constant is 1500 newtons per meter. To find the initial height of the bob, if we take the reference point as this point, and from this geometry, the initial height of the bob is calculated to be h equals L minus L times cosine alpha, or L times 1 minus cosine alpha. Substitute the corresponding numerical values as 0.2 meters times 1 minus cosine 41 degrees, and you get 4.9058 times 10 to the minus 2 meters in the scientific notation. Since we will use these results from now on, we write it in 5 digits. In part A, to find the total mechanical energy of the system, we first find the gravitational potential energy of the system. If we choose the reference point as this point, then the gravitational potential energy is 0 at this point. Since the bob is initially at rest, that is, its kinetic energy is 0, and also initially the spring is unstretched, then the spring energy is 0. Therefore, the mechanical energy of the system at the moment the bob is released will only be due to the gravitational potential energy of the bob at height h. That is, E mech means that mechanical energy equals m times g times h. Substitute the corresponding numerical values into this equation as 2 kilograms times 9.8 meters per second squared times 4.9058 times 10 to the minus 2 meters, which is calculated to be 0.96154 joules, or approximately in 3 digits 0.962 joules. As a result, this is the total mechanical energy of the system at the moment the bob is released. Okay, let's solve part B. When the bob just contacts the spring, that is, at the reference point, potential energy of the system is 0. The spring energy again is 0. Then we have only the kinetic energy of the bob as 1/2 times m times v squared. Therefore, from the law of conservation of the total energy, we find m times g times h, which is the total mechanical energy, equals 1/2 times m times v squared. That is the final energy of the system. Because we are interested in the speed of the bob, we find an expression for v as square root of 2 times g times h. And by the numerical values, square root of 2 times 9.8 meters per second squared times 4.9058 times 10 to the power minus 2 meters. As a result, we get the speed of the bob when it just contacts the spring as 0.981 meters per second. Very good. It is the time to solve part C. When the spring comes momentarily to rest, it assumes its maximum compression state. If we neglect the elevation of the bob, the gravitational potential energy of the system again is 0. Since all the system is at rest, then the kinetic energy of the system is again 0. Then we have only spring energy, that is 1/2 k times x squared. As a conclusion, the law of conservation of total energy gives total mechanical energy, that is m times g times h, equals 1/2 times k times x squared, which is the final mechanical energy of the system. Here x equals square root of 2 times m times g times h over k. Here, for simplicity, we can use the value of m times g times h as we have obtained in part A. Also, if you put the value of k into this equation as 1500 newtons per meter, with the result 3.5806 times 10 to the power minus 2 meters. Hence, the maximum amount of compression of the spring is approximately 3.58 centimeters. Okay, this is the end of the solution of this problem. Thank you for your attention and see you in the next video.